Hello and welcome everybody to the Northwest Quantum Nexus seminar series. Before we have Professor Kaimei Fu introduce our speaker, I wanted to make a few announcements. First, this seminar is being recorded, and so by attending this meeting, you may appear as an attendee in the recording. Your questions and comments in the Q&A session will also be part of the recording. Also, we have a code of conduct with the Northwest Quantum Nexus. The NQN is dedicated to providing a respectful, friendly, professional experience for everyone, regardless of gender, sexual orientation, physical appearance, age, race, or religion. We do not tolerate any behavior that's harassing or degrading to any individual in any form. Individuals are responsible for knowing and abiding by these standards, and we encourage everyone to assist in creating a welcoming and safe environment. NQN reserves the right to refuse admittance or to remove any person from an event at any time at its discretion. And before we do the introduction, I would encourage everyone to visit the Northwest Quantum Nexus website. That's nwquantum.com. You can sign up for our mailing list to be alerted to upcoming seminars and events, and you'll see a list of other activities there as well. So now over to Kaimei for the introduction.
Thank you, Nathan. So it's my pleasure today to welcome Natalie De Leon, who is today's speaker for the NQN seminar series. Natalie is an assistant professor of electrical engineering at Princeton University. She earned her PhD from Harvard in 2011 and BS from Stanford in 2004. And she's been the recipient of numerous times during her faculty career, including the DOE Early Career Award, DARPA Young Faculty Award, NSF Career Award, Sloan Research Fellow in Physics, and the Air Force Office of Scientific Research Young Investigator. Natalie's group has been focused on building quantum hardware with color centers in wide bandgap materials, including the NV center in diamond, as well as other centers in diamond. Her work is extremely broad and interdisciplinary, and you'll see one aspect of it today in her talk on correlating materials analysis with qubit measurements. What I would say is Natalie has emerged as a leader in the field of developing materials for quantum information and tackling some of the hardest problems that qubits are facing from a materials perspective. So with that introduction, please welcome Natalie.
Thank you, Kaimei, for the very kind introduction, and thank you for the opportunity to come talk. Let me figure out sharing really quickly. I think this is the right view. Okay, and if it's not, somebody can just yell at me that you can't actually see my slides. All right, so as Kaimei mentioned, what I'll be talking about today is correlating materials analysis with qubit measurements to systematically eliminate sources of noise. So just to give you a broad overview of what's going on in my group, in general, what we're interested in are atom-like systems in the solid state. So there's been several decades now of work on developing atoms as a platform for quantum information science. And the reason that atoms are really attractive is because you can have very long spin coherence times that act as a nice qubit degree of freedom that you can manipulate and measure. And importantly, they also feature very efficient optical transitions that you can use to connect to these qubit states and read them out and control them. So there's been a lot of really beautiful science done with cold atoms as a platform. And what we're interested in doing is trying to find systems that look very similar to cold atoms, but exist in the solid state, so that you can imagine doing things like integrating them into scalable devices like integrated photonic chips. So these kinds of systems can have applications in quantum information processing and also quantum networks, because you can connect these qubit degrees of freedom to photons and then send those photons over very long distances. And then there's a whole other sort of opportunity that arises because you're in the solid state, where you can also use these atom-like systems as nanoscale sensors. So my group is currently roughly in pursuing sort of three directions. So one is deploying these deploying these atom-like systems in the solid state as nanoscale sensors. What I'll talk about a little bit today is that requires sort of doing quite a bit of surface spectroscopy to understand how to create interfaces between these defects and the outside world. We are also working on developing new solid state defects for long distance quantum networks. And then there's another sort of recent project that has grown up in my group over the last couple of years on trying to look for new material systems for quantum computing, specifically for superconducting qubits. So today, I will not talk about this sort of middle third of what's going on in my group, but I'll tell you a brief story about our work towards nanoscale sensing and surface spectroscopy. And then time permitting at the end, I'll discuss how lessons that we've learned here can be applied towards superconducting qubits. So the physical system that I'll be talking about the most is the nitrogen vacancy center in diamond. This is a defect in diamond where you take 2 carbon atoms out of the lattice and put in 1 nitrogen. So you have a nitrogen next to a vacancy. And it turns out that this NV center has a electronic ground state that is basically mid-gap. So if you look at the energy of that ground state compared to the conduction and the valence band edges, it's roughly in the middle. And then you have sort of a wide enough band gap that you even have space to have an electronic excited state, an orbital excited state that is also very far away from the conduction band edge. So to first order, this basically looks like molecular orbitals, and you can think of this as just a completely confined defect where you don't have to consider the extended lattice around the NV center. And the NV center happens to have an electronic spin. It's a spin 1 that exhibits very long coherence times even at room temperature. So the spin lattice relaxation is something like 10 milliseconds. And then the coherence time is essentially just limited by the surrounding nuclear spin path. So it's how isotopically purified you can make your material. And it turns out that there's a very convenient method of optically manipulating and measuring the spin. So if I just take, something not very much more sophisticated than a green laser pointer, I can read out how many photons per second I get from the NV. And if I shine light on it, I can scatter lots of photons if I'm in one spin sublevel. But if I happen to be in one of the other spin sublevels, I have a spin-dependent intersystem crossing that puts me in a shelving state where the whole thing goes dark. So basically, just by reading out the total fluorescence, I can read out which spin state I'm in. This is called optically detected magnetic resonance. So you see this little dip in fluorescence. And then, for example, you can use this kind of spectroscopy to look at the Zeeman splitting to read out the local magnetic field. And there have been a number of demonstrations in using these as qubits, where you can do sort of coherent manipulations of this electron spin. Because of these properties, there's really dozens of groups around the world, and this is probably an outdated list at this point, that are all looking at this one defect in diamond. And in particular, one thing that people have been really focused on is trying to deploy this defect, to deploy NV centers for nanoscale sensing. So the idea is that because you can have very long spin coherence times, even at room temperature, and you have this convenient room temperature optical readout and initialization scheme, if you combine these properties with the fact that using confocal microscopy, you can really image defects and manipulate them all the way to the single center level, you can imagine now deploying these things as nanoscale sensors. So in particular, if you look at, for example, the dipolar coupling and look at contours of equal strength, you can see that these change very, very rapidly with distance. So you have something that gives you effectively a very, very large magnetic field gradient that you can use for something that looks a lot like magnetic resonance imaging, but at the single atom or single molecule level. So the vision is that you take these NV centers and you put them, for example, next to biomolecules and sense them. And there's been a lot of work recently on doing, for example, NMR of very small volumes of liquids, and also using NV centers as probes of condensed matter phenomena. This is an example of looking at magnetic ordering in a 2D material from Patrick Malatinsky's group, for example, from a couple of years ago. In principle, this can really be pushed down to the single atom level. This is an example from Tim Tamenyaw's group from a couple of years ago, where they used particular pulse sequences to use the NV center to map out the positions of individual carbon-13 nuclei in the vicinity of the NV, and they could really, pinpoint the position of, I think this was 27 nuclei down to the deep sub-angstrom level. So this technology in principle just works, where you can do magnetic resonance imaging at this incredible level of detail using NV centers in diamond. Okay, however, the reason that people haven't ruled the world with NV centers quite yet is that this MRI with NV centers works extremely well as long as you are looking at things deep inside the bulk of diamond in very high, ultra high purity diamond material. But if you want to use the NV center to look at anything else outside of the diamond, you need to get very close in order to get high sensitivity and high resolution. But getting close to this external sensing target also means that you're going to be very close to the surface of diamond. And while we're very good, mankind is very good at making extremely high purity bulk diamond, we are very, very bad at diamond surfaces. And the surface can host a lot of defects that give rise to their own sort of magnetic and electric field noise, and that can obscure the target that you're looking at. And one of the ways that we know this is that if you just look at individual NV centers and plot their depth away from the surface and look at their spin coherence time, so you just plot the Han echo T2 as a function of depth, you see this really horrible power law scaling. So while the NV centers that are around 100 nanometers away from the surface have millisecond coherence times, once you get to within, say, 5 nanometers of the surface, you're more in the microsecond or hundreds of nanosecond kind of range. And each of the different colors here are different diamond samples. So we really do see, that almost everything kind of collapses onto this curve. Okay. So what we'd like to do is, figure out what the surface noise is and mitigate it. And the challenge here is that the NV center is by far the most sensitive probe, but it's very non-selective. It sort of just tells you, oh, I'm looking at a very noisy environment, but doesn't really tell you anything about the microscopic identity of that environment. So you can just do direct surface spectroscopy, but surface sensitive techniques are quite challenging for a variety of reasons. And they tend to probe much larger areas. So it's not a priori obvious that you can find techniques that will give you information that is relevant to the nanoscale environment that the NV center is sensing. So our group set out several years ago to develop techniques to study the diamond surface in detail by just correlating traditional spectroscopy characterization with nanoscale probes. So we tried a very large number of techniques. So you get this kind of alphabet soup of different sorts of X-ray and electron, photoelectron and diffraction and various types of scanning techniques. And the idea was that, okay, most of these things are relatively low sensitivity and probe a large area. But if we can find some material property that correlates with NV properties, then that at least gives us a handle where we can do this kind of direct materials characterization for more rapid feedback. And then we can do something a little bit more sophisticated than just asking the NV center whether or not it's happy. We can, drive the NV center with particular pulse sequences to make it more or less sensitive to different components of the noise and use that to learn a little bit about the character of the noise bath that it's looking at. So one of the things that we learned sort of immediately when we set out on this journey was that much of the community uses oxygen-terminated surfaces to prepare diamonds that have charge state stable NV centers, but different types of oxygen termination can have very significant differences. And in particular, not only can, of course, the chemical nature of the termination be very different, but diamond has a very sensitive surface when it comes to things like plasma processing, because things like etching are very highly anisotropic. And what this means is that the processing can be very hysteretic. So you can have drastic effects on the surface morphology with nominally the same exact processing step, just by having slightly different starting materials. So here's two different diamonds where one of them had a starting RMS surface roughness that was about a factor of 2 higher than the other. But then you can see that here, this oxygen processing sort of revealed a lot of subsurface damage, and then you end up with kind of this crazy surface with a lot of roughness. And what we could see was that even in X-ray spectroscopy, where we were probing things like the unoccupied density of states, we could see an enormous difference between these rough surfaces and these smooth surfaces. So there's really drastic consequences to the electronic structure just based on the surface morphology. So we set out to basically use this X-ray spectroscopy as feedback to figure out how to create very pristine surfaces. And our methodology is basically that, we would find one particular type of damage at the surface, devise a process to remove it, and then, that would introduce its own sort of contamination and damage, and then we would have to devise a process to remove that. So we basically have this iterative processing where we're very careful to maintain a smooth surface morphology, which really requires contamination-free surface processing at every step. So by being very careful, we now have this multi-step procedure where we start with some polish damage, we etch that away, that leaves behind some etch damage, which we can remove with a different type of etching, and then that leaves behind a little bit of implanted oxygen, which we can then remove by by gently graphitizing the top few nanometers of material, which we can then chemically remove, and then finally we do an oxygen anneal that gives us a sort of nice smooth surface. And our typical final RMS surface roughness, this is actually out of date, is below 100 picometers. Now with this improved processing, we're able to get much better coherence times. So basically all of these sort of grayed out points here are the points that I showed you earlier. And then now under our typical best surface, we can get coherence times that are extended by about an order of magnitude. All right, so if you don't want to hear anything about surface processing, you can now take a break and just sort of fall asleep for the next, let's say, 10 minutes. But now what I'd like to do is sort of zoom in on what the differences were between these surfaces. And in particular, what we can do is kind of take this second to last surface where we've done most of the processing, but then still have a little bit of damage at the surface that we've just acid cleaned away, and then compare that to this final surface. So I'll call these the acid clean surface and the oxygen annealed surface. So, the first comparisons that we can do are just look at comparative and B properties under these two surfaces. And we find that this last step is sort of responsible for an extension of coherence by about a factor of 2 or 3. And then we can also do dynamical decoupling to probe the sort of frequency of the noise bath. And we find that we see an improvement from this last step across all frequencies. And in particular, before doing this oxygen annealing, you can see that this T2 sort of saturates with pulse number, which means that you can't just sort of decouple your way away from this noise bath. Whereas after doing this oxygen annealing, we no longer see this saturation. So we can really decouple up to T2s of, exceeding 100 microseconds. We can also take advantage of the fact that the NV center is a spin 1 defect to do relaxation spectroscopy. And in particular, if you look at the relaxation between adjacent spin sublevels compared to the double quantum relaxation where you go from ms equals -1 to ms equals +1. These sorts of transitions can be derived with magnetic noise, whereas these transitions cannot. So by comparing the differences in these two, you can make statements about how much of the noise corresponds to magnetic noise versus electric field noise. And we find that the change in the noise after this last step is predominantly magnetic. We can sort of put all of these things together to do spectral decomposition. And we find that we really do have this very broadband magnetic noise bath all the way from, tens of kilohertz out to gigahertz. Okay, so that's the spectroscopy from the point of view of the NV center. And then now what we'd like to do is look at what the direct materials characterization shows. And we were a little bit surprised to find that when we looked at, for example, near-edge X-ray absorption fine structure spectroscopy, which is, just sort of probing your absorption of X-rays at various edges, when we look at the oxygen edge, where we're probing, this oxygen termination, these were actually very similar spectra. You have sort of the sharp peak here and the shoulder over here. So, these are chemically slightly different, but, quite similar to each other. But one big difference was that if you looked at the polarization dependence of these features, you have essentially no polarization dependence before doing this oxygen annealing, and then a really dramatic polarization dependence afterwards, indicating that this final surface has a high degree of order at the atomic level, whereas this initial surface is highly disordered, which washes out any kind of polarization dependence that you would be able to see. Additionally, we were able to show that with ultraviolet photoelectron spectroscopy that this final oxygen annealed surface had much higher positive electron affinity. And we actually sort of resolved a long-standing kind of puzzle in the field that if you just calculated what a hydrogen terminated electron affinity should be, you got basically the right answer. Whereas when people calculated oxygen terminated electron affinities, they got a value that was around an EV or even 1.5 EV, larger than what people measured. So I think what we showed here is that the degree of disorder at the surface really matters quite a bit, and that you generate a lot of electronic defects that have drastic consequences for the electronic structure. So this value of 2.14 EV is much closer to the calculated value. And just to show you that we have really a very high degree of control over this surface termination, we can kind of toggle back and forth between these two different surface conditions. So we can start here with an NV center that has a spin coherence time of something like 10 microseconds at 7 nanometers. We do this final oxygen annealing step and extend the coherence by about a factor of 3. And then we can thermally reset the surface and see that the coherence time goes back. And then we can do a last oxygen annealing step and recover almost all of the coherence. And you can see that this is true for every NV center that we look at. Okay, so to just summarize this sort of initial story, we've been able to make a new diamond surface termination that's very highly ordered. And we're able to realize NV centers that are within a few nanometers of the surface with coherence times that we can decouple out to past 100 microseconds. And then sort of as a broader picture, we're really able to use these complementary spectroscopy techniques in order to discover sources of noise and then mitigate them. So far, all of the kind of NV spectroscopy that I've shown you is very traditional. We were basically just, looking at coherence times. So I thought I would tell you a brief story about how much more you could learn from these decoherence curves. In particular, what we were able to see in these detailed surface studies is sort of a bath of spins at the surface that we could address by double electron-electron resonance. So the idea is that, you do your standard Hahn-Echo pulse sequence at the NV center, which cancels out any kind of quasi-static noise that's on these relevant timescales. And then if you have another frequency selective pulse that drives the surface spin bath in the middle here, then you cancel everything other than these surface spins. So formally, this is very similar to a free induction decay measurement of these surface spins. So what we're able to see is, okay, we do this Hahn-Echo sequence on the NV center, and we get a coherence curve that looks like this. And then we add this additional kind of double we add this additional pi pulse to do our double electron-electron resonance measurement, and we get this red curve here. And then if we just divide these two, then we get this guy here, which is sort of our surface spin free induction decay. And then we use this to extract our Deer coupling rate. And if we just plot this Deer coupling rate as a function of depth, you can see that it goes up as you go closer to the surface. This is a number of surfaces that were all prepared the same way, and these are surfaces that were prepared in different ways. So you can see that the overall scale of this coupling changes, but this general depth dependence is pretty universal. Okay, so even from just these plots, there's already a couple of puzzles in this data. So the first is that if you have coupling rates that are if you just calculate basically the Deer spin density that is associated with the coupling rates that we see, the NV center distance to the surface is actually much closer than the Deer spin to Deer spin coupling distance, or the Deer spin to Deer spin distance. So that means that on average, you should really be seeing sort of a stochastically varying population of Deer spins as you approach the surface. And instead of seeing this kind of nice linear dependence, what you would really expect to see is something that just gives you much larger variance as you approach the surface. So that was one puzzle. And then the other thing that we can do is sort of use the surface spectroscopy to directly look for correlations with features and this Deer signal. And what we were able to see is that in samples that have a high degree of Deer signal, we also see this dangling bond peak down here at 282.5 eV. Okay, but there's a lot of things that change between this acid cleaned and this oxygen yield surface, as I showed you before. So what we can do is another kind of in situ annealing sequence that is different, where we show that if you just anneal in situ at around 600, 650 degrees, nothing much changes at the oxygen edge, nothing much changes at most of the carbon edge. But then if you zoom in on this dangling bond peak, you can see that it disappears. And similarly, what we show is that if we then sort of reproduce this vacuum annealing, we can really suppress this Deer spin density by, a factor of several by doing this vacuum annealing. Okay, so now let me re-bring up this puzzle. So here, if you just fit these orange points to some expected Deer spin density, you get something like a linear spacing between spins of around 14 nanometers, which means that the NV centers that we're looking at are much closer to the spins on average than they are to each other. So again, it's very surprising that you just get this scaling as opposed to something that sort of expands where you can accidentally get lucky and get very close to Deer spins, or you can get very lucky and be very far away from them. Okay, the second puzzle that we found is that if you look at this coherence decay curve very carefully, and you fit it to a stretch exponential, e to the minus gamma Deer tau to the n, the sort of standard theory that you would write down for this free induction decay is that you should have a stretch exponent of n equals 2. And n equals 2 is a very, very poor fit to this data. And you can see that it's really much shallower than that. And in particular, if we do this sort of fitting and we just let this n vary without putting any bounds on it across many, many samples, we see that there's sort of a general depth dependence where we get smaller n's for shallower depths. And then more surprisingly, we see a large number of these n values that are even below 1. And there's actually sort of no way to write down a simple theory that gives you an n that's less than 1 as long as you have well-behaved monotonically decreasing noise. Okay, so that's puzzle number 2. Puzzle number 3 is that given the Deer spin densities that we infer, we should see coherent coupling to Deer spins a large fraction of the time. But actually, we only observe coherent coupling in a couple percent of NV centers. And as one possible solution to all of these puzzles, we could sometimes see this coherent coupling signal blink on and off. So as we continued measuring the same NV center, if you just parked at one particular sort of point in this oscillation, you could see it sort of show up and then disappear and then show up and disappear. So there are some sort of surface spin dynamics that are at play here. Okay, so it's worth thinking about how you might be able to generate a stretched exponential decay. So in particular, if I have an NV center that's staring at some high density bath, that gives me, some coherence decay where I have an n equals 2, but I have some characteristic timescale. But then if I have a low density bath, I will also have an n equals 2 decay, but it has a different effective timescale because you're looking at less noise. So now if I take the average and put these two things together, then I can get, kind of this funny looking curve that essentially, will eventually turn into a curve that looks like you have a single stretched exponent that is less than 1. Okay, so if I can have some kind of configurational averaging, this will give me an exponent that is below this bound of 1. And sort of separately in my group, we had been thinking a lot about photoionization of defects in diamond. It's well known that if you just look at NV centers and sort of pump them hard enough, they will photoionize into another charge state. So, you can get 2-photon ionization, for example, that puts your electron into the conduction band, and then you convert from NV minus to NV0. So one plausible model is that these spins at the surface are also spatially moving around in 2 dimensions. So if we now do just some simulations where we create, some random assortment of these spins, or some random configuration of these spins on the surface, and then simulate the different coherence decays for all of these configurations, we get a bunch of cosines, and then when you average all of these cosines together and try to fit to a single exponential, you get something that looks like n equals 2 for very, very deep NV centers, because they just see sort of a Gaussian noise bath. But as you approach the surface, what the NV center actually sees is something that really looks like a 2-dimensional bath. And this gives you an n equals 2, an n that is 2/3. Okay. So from the simulations, we then worked on an analytical model where what we actually discovered is that this fit to a single exponential is actually just the incorrect model. And in particular, what we're seeing is just a critical crossover time between a time interval where you see this exponent of 2 over to a time interval where you see this exponent of 2/3. And the general argument is that you can think about sort of the contributions of all of these different surface spins at a particular time as being related to the total dipolar coupling strength. So you have this circle, or I guess the sphere, that expands over time, that encompasses everything that has interacted strongly enough for long enough time to critically couple, to coherently, to strongly couple and coherently couple with the NV center. So at very short times, you just see small contributions from all of these distance spins. And then as this volume kind of expands, then you eventually start to encompass, individual spins that you get these coherent coupling cosine curves from. So basically, the general picture is that at very short times, the NV center just sees all of these distance spins at the surface. And then as this volume intersects the plane of the surface, you then start to integrate over the area law of the surface, and you see something that looks like a 2/3 exponent because you have this 2D bath. So this exponent is basically going to be the dimensionality of the bath divided by the strength of the interaction. Okay, so now armed with this analytical model, we can go back into our data and actually look for evidence of this by intentionally oversampling the coherence decay quite a bit. So these are not super easy plots to look at because they are log plots. And the advantage here is that you can just read off the exponent by looking at the slope of this curve. And you can see that indeed you see at short times, we have something that really fits to an n equals 2. And then at long times, you see something that bends over to an n of 2/3. And the really interesting thing is that this crossover time should just be set by the depth of the NV center away from the surface. And what we find is that when we compare the depth that you infer from this crossover with the depth that we separately measure by nanoscale NMR, these numbers really agree to sort of remarkable consistency. Okay, so everything that I told you is actually quite generic to just interacting spin systems in 2 dimensions. And so this is something that you should be able to see in, ensemble NMR or ESR. However, people do not see this critical crossover time generally. And the key kind of feature here is that this crossover time is observable because the NV center is a separable probe. So this time scale is just going to be determined by, the closest length scale between 2 possible spins. So in anything that has sort of lattice scale separations, this time is going to be so short that it is not observable. So here, because we can set the distance arbitrarily, we can also set the time scale arbitrarily, and that allows us to experimentally observe this critical crossover time. Okay, so as a brief summary, we showed that the NV center is this very beautiful local probe of external spin systems. And just by doing very careful measurements of this decoherence, this exponent gives you a probe of the dimensionality and the dynamics of the system that you're looking at. Narrowly for people who are experts in this field, what we showed is that these surface spins are configurationally averaging, which means that they're physically hopping around. This has many implications for trying to utilize them as sensors. And then I'll just emphasize again that this ability to choose the distance of your NV center is really key. And it would be interesting to kind of deploy this kind of methodology in scanning NV measurements where you can dynamically change the NV distance. Okay, so just as a brief outlook or overview of other stuff that's going on in my lab, we've also done a lot of work studying charge dynamics of NV centers and other color centers. One thing that we're working on actively is trying to prepare truly pristine surfaces, and we've built an ultra-high vacuum chamber with a surface spectroscopy and preparation chamber attached to a cryogenic confocal microscope, also in ultra-high vacuum. And we're able to sort of look at NV centers under really pristine surfaces that we can prepare in UHV. And we're currently studying the impact of contaminants on the noise bath that shallow NV centers see. And then finally, what you would really like to do to turn these things into versatile quantum sensors is to be able to attach things deterministically to the surface of diamond. And diamond is quite inert and difficult to functionalize. So we're currently working in collaboration with Rob Knowles' group in chemistry at Harvard, who's an expert in a field called photoredox catalysis, which really is a field that's only existed for the last 15 years or so. And it turns out with these very modern catalysts, we're now able to do a very gentle, wet chemical functionalization of the diamond surface that really expands the scope of things that you can attach to the diamond. Okay, so now with the remaining, I guess, 10 or 15 minutes, I'm going to completely change gears and tell you about how we can apply some of the lessons that we learned in trying to do the systematic study with NV centers and diamond to a completely different physical platform, which is superconducting qubits. Okay, so the superconducting qubit is a very successful platform for quantum information science. A lot of the largest systems that people are currently working on in terms of large-scale processors are built on the superconducting qubit. It's really enabled a lot of very impressive demonstrations involving quantum chemistry. And then, of course, there was this sort of big landmark demonstration at Google a couple years ago on quantum advantage for simulating random circuits. Okay, so it's a really exciting platform. But one of the things that people tend to not talk about is that there was this really nice march in single qubit coherence for about a decade and a half, where people had a number of design improvements and were able to sort of push the coherence time of superconducting qubits to around 100 microseconds. But then since about 2012, people have not really improved this lifetime. So the last record for a planar device in terms of the quality factor of a superconducting qubit was set in something like 2012. And it's generally believed that this is just limited by dielectric loss in the material. Okay, and there was a lot of evidence that this loss is specifically related to surfaces. So if you just look at the bulk losses that are set by measurements of microwave resonators made out of sapphire, that bulk loss should allow for quality factors of something like 10 to the 9. But what people usually get is something like a couple million. And in particular, if you look at many different qubits with varying mode overlap with the surface, you can see sort of the scaling that implies that these losses get worse and worse as you make these qubits smaller and have more mode overlap with the surface. So let me just tell you one very brief cautionary tale based on our work in diamond. So a lot of people attribute the surface loss to two-level systems. And then they have done a lot of work just trying to very carefully characterize the two-level systems that they can see directly with spectroscopy. So I just told you this whole story about how we can do something similar with NV centers, where we can use double electron-electron resonance to look at these dark spin defects at the surface. And this is also something in my community that people have focused a lot on as a source of the surface noise. However, when you look at the correlation, and then when you look at the correlation between the decoupling rate and coherence time, you do actually see this inverse correlation that looks very suggestive that maybe these deer spins are responsible for this poor coherence. But actually, it turns out that this apparent correlation is just a correlation between both your surface spin density and your T2 with depth. So basically, the surface spins exist at the surface, and T2 gets worse as you go close to the surface. So it looks like you have a correlation. But we can do a lot of processing that, for example, changes the decoupling and doesn't change the T2, or changes the T2 and doesn't change the decoupling. So this sort of shows that you can get these kind of false signals in terms of correlations with the thing that you care about, which is qubit coherence. Okay, so we set out to try to systematically study the possible losses in the system, and we were working with Andrew Hauk's group, and his group was primarily working with this material system. So they had sapphire substrates. They make a Josephson junction out of aluminum oxide, and then they were making the capacitors and resonators of their transmon out of niobium. Okay, so based on this material system, we generated two hypotheses for dielectric loss, largely together with Bob Cava, who's in chemistry at Princeton. The first is that you can just have contaminants on the substrate. And if we just did sort of AFM of the typical sapphire substrates that Andrew's group was using, we found that they looked very, very messy. So basically, things out of the box are just going to have a lot of stuff on them. And if you're not very careful with how you clean it and prepare the substrate, then you just have a lot of junk that leads to very classical dielectric loss. The second thing that Bob pointed out is that niobium has extremely complicated oxides. So you can get essentially any stoichiometry of niobium oxide that you can dream up. And because you have all of these different phases of niobium oxide, the hypothesis is that this can just lead to things like resistive loss at the surface and dielectric loss. Okay. So we worked on trying to do better sapphire substrate preparation so we can kind of clean these things, and then we can also etch away some of the polish damage layer, and then we can even do some high temperature annealing in order to recover these atomic terraces. One thing that we found was that there is this sort of persistent zinc contamination that we didn't entirely understand, but we could just do this etch to remove a little bit of the surface, and that would get rid of this contamination. And then on these pristine substrates, what Bob pointed out was, okay, niobium is really terrible, so maybe you should just try something else in the periodic table that has better oxides, and the suggestion was to try tantalum. So we can do tantalum deposition on sapphire. We actually get very epitaxial-oriented growth. One of the tricks here is that normally if you make thin film tantalum, you actually get the wrong phase. You get this very low TC beta phase. And you just have to do, high temperature growth or seeded growth in order to get the right alpha BCC phase of tantalum. So we're able to get this nice oriented growth with some grain structure. And then if you zoom in on the top layer, you can indeed see this very thin amorphous oxide. And it's around 2 to 3 nanometers, and it's really just Ta2O5, sort of regardless of any kind of processing you do. So tantalum oxide is very similar to aluminum oxide in that you just get this kinetically limited layer that is extremely robust and very chemically inert. And it's also very robust to differences in microstructure and different sputtering conditions. Okay, and one thing that we can do in order to directly compare these oxides is do depth profiling by doing XPS at different energies at the synchrotron. So this is in collaboration with a number of scientists at the National Synchrotron Light Source 2 at Brookhaven. And they had done this nice work with Andrew Hauk's group where they showed that in niobium, you see that the suboxide, that there are a lot of suboxides and different stoichiometries of oxides, and they sort of penetrate very deep below the niobium oxide interface. Similar analysis of suboxide and we see a very sharp interface sort of to within our modeling error. Okay, so we have this better oxide from tantalum and better substrate preparation, and then sort of the last step is that we can, look at exactly what we're doing with the fab. And there were many iterations where we had a lot of surface roughness, just because of exactly how we were doing either dry etching or wet etching. And we finally developed a procedure where we have very smooth edge morphology, where the hypothesis here is that this roughness can concentrate field and give you an apparent higher surface participation ratio than you are expecting. Okay, with all of those improvements under our belt, we are able to make qubits that have lifetimes exceeding 300 microseconds. And then we can also see coherence times that are up to around half a millisecond with dynamical decoupling, and that these parameters are very robust across devices and over time. So we're not just cherry picking kind of a single data point. We really do see that we have T1s that are, exceeding 200 microseconds and even as high as 400 microseconds in some cases. Okay, so this was sort of our first, volley of let's see if we can replace the materials and do a little bit better. And we were able to kind of break through this record that had stood for 8 or 9 years by a factor of about 3. So now what we'd like to do is take a step back and actually just do systematic studies to figure out what it is that is likely leading to the remaining sources of loss. So we turned to try to just make tantalum resonators with the idea that we could do much more rapid measurements. So we sort of eliminate the variation in the junction fab. These tantalum films are much more robust to different types of processing than the aluminum oxide Josephson junctions, so we can kind of subject them to more things. We can access a much larger temperature and power range to try to understand, how these things vary, and use that to find microscopic sources of noise. And then we can multiplex these things, so we can just put 8 resonators on a chip, and as long as they're frequencies, as long as they're scattered in frequency, we can kind of independently address them. So in these resonators, we're able to see something that a lot of people have observed, which is that their quality factor increases as you apply more microwave power. And the model that most people write down for this is that you have saturation of 2-level systems. Okay, but to try to maybe tease these things apart much more quantitatively, what we can do is a full power and temperature dependence. So we just look at a particular power, we scan the temperature, and then plot the quality factor. And what you can see is that there are sort of 3 salient features to this data. And then we take this curve at many different powers. So the 3 salient features of this data are that at high temperatures, you see that we approach the temperature that is associated with the superconducting gap, and then you just get losses that are related to quasiparticles. And then from this range, from about 100 millikelvin to 500 millikelvin, you see this increase in Q of about a factor of 2, and that's consistent with just thermal population of TLSs. So you get this slight decrease in losses. And then sort of to our surprise, you also see this increase in Q at low temperatures as you go down in temperature. And it turns out that this is very simply explained by a model where the TLS saturation parameter decreases at low temperature. So the T2 is expected to have a 1/T dependence, and that just means that at this temperature, you need a lot less power to saturate the TLSs. Okay, so we can fit this entire sort of family of curves with just a few fitting parameters where we have 3 loss channels, some quality factor that's associated with TLS loss, something that's associated with these equilibrium quasiparticles, and then a ceiling on top of all of this stuff that's power and temperature independent that looks like a Q other. Separately, as another check on some of these fitted parameters, we can look at the shift in frequency of the resonator as a function of temperature, again with the same model with TLSs and quasiparticles, and then some additional source of loss. And then we can cross-check these fitted parameters across these different data sets, and we find that we get things that are actually remarkably consistent. So for different resonators that have the same surface participation ratio, we look at these different data sets, and we find that the QTLS that we fit is very similar. And I'll just note as a word of caution for the rest of the community that if we just took a single one of these quality factor versus power curves, we systematically overestimate the Qs associated with TLSs. So I think that is a decidedly lower quality measurement. Okay. And then finally, what we can do is, look at many different devices with different processing histories and different surface participation ratios and sort of plot them all together. So the gray points here are from Chen Wang's paper that I showed you earlier. And then this is somewhat messy, but basically each of these different colored data points is some different surface processing condition. This raft of points up here is the qubits from our Nature Comms paper. And what we find is that there's a general scaling with surface participation ratio where we're riding something like a factor of 3 better than all of these aluminum and niobium qubits down here, and that we do see these surface-related losses. Okay, so in conclusion, we saw a big leap in performance with pretty simple material changes, and I think the lesson is that there's probably a lot more material space to explore. The current devices that we have are TLS limited, and we also have some evidence that we actually have bulk losses for the lowest surface participation ratio devices that are sort of comparable to these TLS losses. And what we're now setting out to do is really systematically study how different types of processing and different material properties affect these fitted parameters, which give us a sense of, how much of the losses are really due to TLSs versus other sources. Okay, so with that, I will wrap up. So the work done on shallow and V centers was led by Peace Songtawesen and Leela Rogers in my group. And then a lot of the work done on these surface spins was done in collaboration between my group and Misha Lukin's group at Harvard with Bo Dwyer, Ilana Urbach, and Dola Blufstein. It was kind of a fun COVID project that we had been ignoring the fact that these decoherence curves didn't make sense for several years. And then when we were all stuck in quarantine, we started looking at these curves much more carefully together. And then I have a very large number of collaborators to thank for that project as well. The superconducting qubits work was led by Leela Rogers, Avik Dutta, Trisha Madhavan in my group, and Alex Place, Wang Li, Yochi Gang, and Kevin Crowley in Andrew Hauk's group, and was done in collaboration with Andrew and Bob Kava over in chemistry. And we're now working on this really exciting broad collaboration in the context of this DOE NQIS Center, the Co-Design Center for Quantum Advantage, together with a number of groups at Yale and also at Brookhaven and other institutions associated with the center in order to really move rapidly in understanding these tantalum qubits. And then I'll just end by saying that there's a lot of exciting opportunities to do quantum research at Princeton. We launched the Princeton Quantum Initiative in 2019. This is now actually an outdated list of faculty, so there's really a very large set of faculty that are looking at various aspects of quantum science. And we have a very large presence of the Co-Design Center for Quantum Advantage on campus. And we have a PQI postdoctoral fellowship where the applications are due December 1st. So I encourage you to reach out if you're interested. And with that, thank you for your attention, and I'd be happy to take questions.
Great. Thank you, Natalie. That was a fantastic talk, and I really like seeing how, by looking at the materials, it's remarkable that you could impact two very, very different qubit hardware structures. I'm going to let people have some time to think about what questions they want to ask, and I'm going to ask you a few questions in the meantime. The first one is a bit broad. What would you say is the highest impact application facing these single atom sensors, and what is the biggest challenge to get there?
Yeah, that's like a real minefield. Yeah, so I think there's the way that I see it, I think there are two really exciting frontiers with NV centers. So one of them, which is I think the one that most people are sort of really pushing on, is using it as a local probe for condensed matter phenomena. And there's been a lot of beautiful work that people have done. And I think the real issue is that there are not that many non-invasive probes. So most of the things that you do to look at at condensed matter systems is like you put electrodes down and you look at transport. You can, put gate voltage that scan around, and things like that. So there are, of course, also spectroscopy techniques, but those tend to not have as high spatial resolution. So the real prize is if you can do something like, current sensing, magnetic field sensing with this NV center very close by without perturbing the system that you're looking at. The hope is that you can really learn, new things that we can't access with tools right now. And there's been a lot of really nice progress along those lines where people are building, for example, scanning NV magnetometers where they, fabricate these cantilevers and then scan your NV center around. And my understanding is that actually the main limitation in those experiments right now is that they can't get very good NV centers in these cantilevers. So they're surprisingly far from the surface that they're scanning, and their coherence times are really poor. So if you really could take advantage of all of this quantum control, right? If you could just do dynamical decoupling, get very long pulse sequences, do AC magnetometry, then I think you could learn a lot. But right now they're sort of stuck at a level where they're 15 nanometers away doing DC magnetometry because they're unable to solve some of these hard surface challenges in combination with all of the really complicated fabrication that they have to do. So that's one kind of clear outstanding goal from a material standpoint. I think the other big space that I'm pretty interested in is trying to do single molecule sensing. So, we learned a lot in the biophysics community just by learning how to do single molecule imaging and creating these environments that are relatively artificial, right? Like you take a protein, attach it to a surface, and do like FRET microscopy. But it's really good for generating kind of new hypotheses for things to look at in cells. So if you could really do magnetic resonance imaging, without having to like fluorescently label and things like that, that would obviously be super exciting. But there's a very large number of hurdles to overcome before you get there. A very small part of which I talked about today. But you also have to figure out this like surface functionalization stuff, for example.
Great, thank you. I think that gives some perspective. My next question is probably super naive. Your last plot, which showed your temperature dependence on the Qs, would it ever just make sense just to try to go to lower temperatures? Do we expect the superconducting qubits to work better just going colder? Is that an option?
Yeah, that's an interesting question. Right. So what have we actually shown? We've shown that the quality factor goes up even for powers that are effectively single photon powers because you have these TLSs that are very, very easy to saturate. So I guess my answer would be that yes, it does seem like you keep on getting better at low temperature, but it remains to be seen whether or not the fact that you have a bunch of populated TLSs affects your coherence time. So just because you found a way to enhance T1 doesn't mean that you can really capture that in T2. And I guess right off the cuff, I would say that you would think that it would be a problem that there are these things that can still spontaneously emit into your qubit at the qubit frequency. But maybe that is too glib of an answer.
Okay. So now people have had time to ask some questions. So we'll move to the audience questions. So from Brent Van de Vender, he asked, do you know if any groups have successfully imaged complicated molecules at any level with MRI-like techniques using NV sensors?
I'm pretty sure that the answer is no. I don't know if I just got in trouble. But so basically, at the surface, the coherence times are pretty bad. So being able to do some of these long pulse sequences and, varying your field and all of that stuff is quite hard. So most of what people have done is just looked at NMR, where you can look for noise that's associated with the Larmor precession frequency, but then you're not really doing any like spatially resolved mapping or anything like that. And there, people have been able to see pretty small numbers of protons and nuclear spins, you can get down to molecules that are, let's say 30 nuclear spins or something like that. And that was about state of the art a few years ago. We have not gone back to that experiment since making a lot of the improvements that we've shown in the last few years.
Okay, thank you. And then another question about surface processing from Peter Shushko. He says, I noticed it starts with argon chlorine. Does this treatment introduce new defects? Are there plausible, milder alternatives?
Yeah, so the chlorine definitely implants chlorine, but it's a very, very low bias voltage. So you just have to get rid of that. So that's why we do this iterative processing. So we start with argon chlorine and then follow it up with oxygen. When we do this oxygen etching, it's, we take away a micron or several microns of material. So we don't think that there's any impact of the original chlorine etching. The main reason that you do chlorine etching is because it's one of the few kind of nicely isotropic etches of diamonds. So it smooths out, it's one of the few things that will actually smooth out your surface rather than, revealing roughness. So it kind of helps out with any remaining polish damage that you have.
Okay, and as a follow-up question, once the surface is treated, how long does it stay clean and ordered? And what environment is necessary to retain this clean ordered property?
So we don't see any evidence that the actual surface termination degrades over time. I should be a little bit careful, but we've definitely taken samples where we characterized all the NV centers as a function of depth, put it in a cabinet for like a few years, take it out, and everything basically still looks the same. We can even look at the exact same NV centers because you can just do this confocal mapping very well. So I think the oxygen termination is very robust. The thing that does happen a lot is that these things just get dirty. So if you don't know how to clean it in a, in the right way, then you just get like buildup of fluorescent junk on the surface and things like that. So, and that is essentially unavoidable unless you really stay in UHV. Well, I don't know, even in UHV, I think the time for a monolayer of stuff to deposit on your surface at 10 to the minus 11, it's like days. It's not, it's not infinity. So you're just always going to have stuff, and then you just have to figure out how to clean it off.
Just as a quick question, does the stuff, you said the functionalization stays the same, the stuff that's on the surface, won't that affect the properties of the NV center, or it doesn't?
Well, I guess my specific statement is that we just clean that off with something that we have no evidence actually affects the surface termination, right? And then we know that under that cleaned surface, everything looks fine.
Okay,
the junk is terrible. Like you can't even image your NV centers. So it's sort of a hard to answer question.
Yeah. All right, well, I think we're at time. I want to thank you again on behalf of the NQN for taking time out of your busy schedule and giving this great talk and introduction to this field. Thank you so much.
Thank you.